Hi, and welcome to Codex. Our speakers today are Doug Hardin and Nate Tenpas. Professor Hardin earned his PhD from Georgia Tech in 1985 and is a professor in both the mathematics and the biomedical informatics departments at Vanderbilt University. Nate is his doctoral student at Vanderbilt. Professor Hardin is an expert in discrete minimum energy problems, inverse problems, wavelets, machine learning, and bioinformatics. Today, they will tell us about linear programming bounds for discrete periodic energy problems. Take it away, Doug and Nate.
Okay, great. So Nate's hiding, but we're going to be tag teaming back and forth at random. Secondly, please ask questions. There will be parts that we can zip through. We can adjust the talk. If we don't get to the end, that's fine with us. So it's more important that if something's not clear, to please ask. Also, I've kind of divided the talk into two parts. This area of discrete minimum energy problems is kind of have been a long time collaboration with Ed Saf in the math department here, now more than 15 years. And so most of our work has been on asymptotics for large numbers of configurations. So I wanted to set a little bit, and also that's our motivation for a number of things. So I'm going to do a little bit of a review of quickly of some of the asymptotic results, and that will also allow us to set up some of the notation for okay, there we go. So first of all, what we mean by the discrete energy problem is we have typically a compact set X where points are restricted to live in RD. We have a kernel. Right now, it just needs to be lower semi-continuous and symmetric. In the next slide, we'll need to add a condition that it's positive definite with respect to a class of sign measures. In any case, the K energy of a finite set of points in X is this sum. It's the sum of K, Xi, Xj, summed over all pairs where I is not equal to J. So there's a factor of 2 depending on how you interpret that sum. It doesn't really matter here. We're often interested in ground state configurations or configurations that minimize this energy. And so we'll use calligraphic E to denote the minimum energy of n points restricted to X. The lower semi-continuity here will, in fact, imply that this infimum is a min together with the compactness of X. And we'll refer to a configuration that achieves this minimum energy as being K optimal. A lot of our work has been with inverse power laws, Riesz potentials, so we're interested in how what changes when you change the power S. We'll see a lot of inverse power laws. For example, in R3, when S is equal to 1. This would be the electrostatic Coulomb interaction. So we'd be talking about minimizing the energy of n equally charged particles interacting through a Coulomb. As S goes to 0, the natural, of course, this goes to 1, but then the linear term in S involves the log of the reciprocal. The logarithmic kernel is both the harmonic kernel in the plane, as well as kind of in any dimension, the limit as s goes to 0. So the logarithmic kernel is also important. For us, especially important today, we want to discuss the case where our interactions are Gaussian interactions. And we're interested in, for any parameter C, the Gaussian interaction between points. And for large n, there's a lot that we can't yet say, but okay, so some common choices. There's a lot of work on the sphere in various dimensions. In 2 dimensions, there particularly will be the focus of today. This is just a numerical simulation that we've done, gradient descent on 30,000 points. You allow them to go to a local minimum, and this is typically the kind of picture you get. Here I happen to pick s equals 3, but on the sphere, the qualitative structure of the points is going to be very similar. Now, what we're showing here is for these 30,000 points, we're showing the Voronoi tessellation. So in other words, this is the partition by the nearest neighbor, the partition of the sphere by the nearest neighbor function for these 30,000 points. There's also there's a coloring given. Most of the points have 6 nearest neighbors. Their Voronoi cells are colored in green. Not only do they have 6 nearest neighbors, but if you look at the histogram of the distances, most points have a nearest neighbor distance that's almost the same. There's a cluster, the histogram has peaks at distances that are corresponding to these very regular hexagons. Now, if we color them blue, if there are 5 nearest neighbors, and red if there are 7 nearest neighbors. And so it's interesting, this distribution of pentagons and heptagons, but these, okay. The preponderance of the hexagonal structure is very much related to what we're going to talk about today. Okay, that was.
Hey, Doug.
Yes, go ahead.
Yeah, just a quick question about
Yes.
that picture.
Okay.
So the blue and red hexagons and heptagons.
Yes.
They appear to make curves.
Oh yeah. Okay. This is an active project that right. So there's a couple of things. We believe these are called scars in the physics literature. They are very closely related to what are called grain boundaries in things. So right now we can't. Yeah. So we have a conjecture about where they begin showing up in the asymptotics as n goes to infinity, about properties of these. We're not quite able, we'd love to model them. There's probably PDE kind of models where we have regions of very uniform behavior depending on the actual cardinality. And then we have kind of cracks in the uniform. We can't say anything precise about these, but we're working on it, and other groups are too. So yeah, there's a lot of cool things that we're going to be working on more kind of smaller scale things today, but okay.
Awesome, thank you.
Yeah, so You pushed a button for me there. So yeah, there's a lot of cool stuff that we can't say anything. Anyway, quickly, classical tools from potential theory allow us to say to get first order asymptotics when there is a finite energy measure. Okay, so let me just say that. So now for simplicity, I want K to be a positive definite kernel with respect to signed measures for which these integrals are well defined. Okay, so in any case, so we consider what's called the continuous energy problem, the problem of minimizing the energy of probability measures, Borel probability measures supported on X. So this would be for a given kernel, this would be the energy of that measure. And you can see that it's, okay, well, we'll see in just a second. If there is some measure for which this integral is finite, so some Borel probability measure, that's something about how singular the kernel K is with respect to the set X. And so if there is one for which it's finite, then the positive definite implies that there's a unique minimizer of this energy, and that's called the equilibrium measure. And the equilibrium measure will determine the first order asymptotics, both in the actual minimum energy as well as telling you how for large n the configurations are distributed on a macroscopic kind of density scale. So if we have such a kernel that has an equilibrium measure like this, and you take any sequence of K optimal endpoint configurations as n goes to infinity, then the minimum energy goes like n squared times this energy, and it's you can think of it as approximate. Well, okay. Anyway, it tells you the minimum energy dominant term of correct. It also tells you that what's called the empirical measures, or in other words, if you turn an endpoint configuration into the natural probability measure, okay, that these empirical measures converge to the equilibrium measure in the weak star sense. So in the sense of density. So you integrate against a continuous function and sample the functions at omega n star, take an average, that will converge to the integral of the function with respect to mu k. So that's a great result. Okay. Now, in particular for Riesz potentials, this Frossman's lemma tells you that when S is less than the Hausdorff dimension of X, that's precisely when you can find a finite energy measure. If S is bigger than or equal to the Hausdorff dimension, there's no probability measure supported on X, no Borel probability measure supported on X, for which the Riesz energy is finite. So this is in potential theory is saying that what's called the capacitary dimension is the same as the Hausdorff dimension for compact sets X. Okay, so our work, Ed Saf and collaborators, has been on the hypersingular case when S is bigger than or equal to D. It's a little more technical when S is equal to D, so I'm just going to give a sample, the result, our main result when S is larger than the dimension, the Hausdorff dimension of the set. First of all, we need more structure to get a result. So we need X to be D-rectifiable. Then in this case, we can prove that the points become uniformly distributed with respect to Hausdorff measure. So they're, okay. And also the minimum energy now is given by a constant CSD, the size of the set measured in the Hausdorff dimension, and then times n to the 1 plus S over D plus, this is the lower term. We'll find out that the CSD is very much related to the local structure. So let me give just a quick picture that demonstrates this. So so we call this theorem the Poppyseed bagel theorem because we like to show these pictures on tori in R3. And so when the parameter S is 2 or bigger, so this is just the torus with finite surface area. So this is a 2 rectifiable set. I mean, it's, it's even more, it's nice. It's a infinitely differentiable manifold, but it's nicer than a general 2 rectifiable set. But the result says that when S is less than 2, then the points become distributed according to the equilibrium measure. And here and in fact, when S gets close to 0, you can prove that the equilibrium measure on a torus is supported on the outer part, and is 0. It's supported on the outer part of the thing. So things are really pushing away. This would be the Coulomb case. When S is 1, it's non-uniform, it's denser on the outside. When you get to 2 or bigger, then the number of points asymptotically in some nice subset of the torus will be proportional to the surface area of the torus. So these are uniformly distributed with respect to surface area. Now, I want to begin the real part of the talk. Okay, so so now we want to work in a context of periodizing of periodic potentials. And so first of all, in physics, lattice can mean different things, and in mathematics, lattice can mean different things. So for us, a lattice in D dimensions will be the integer linear combinations of some basis in RD. Okay, so the same as taking an invertible D by D matrix and applying it to ZD. If you mod RD by lambda, then a canonical choice of fundamental domain is applying A to the half open interval 0, 1D. Now in the periodic topology or in the torus topology, omega is going to be compact. Okay, so whereas as a subset of RD, it's not, but okay, we'll be doing that. When we have a potential that decays sufficiently rapidly, with sufficient decay, then we'll consider the periodized potential that you get by summing over all possible lattice translates. So one way to think about this is that this the f of x minus y, or this kernel, is the energy that's required to place a unit charge at x in the presence of the infinite periodic collection of unit charges given at y plus all of the lattice translates. Now, there's some kind of fun, because this is periodic, you can either assume all the points are in the fundamental domain, or you have endpoints wherever, right? Okay. So in the lattice, in kind of the language of number theory, when you periodize a Reese S potential when S is bigger than D, you get what's called an Epstein zeta function for the lattice. These are these kind of lattice sums. And a big conjecture for us, this goes back even, this essentially is a conjecture of Edsaf and Arno Couillards from 95, I think. It's a little different because we didn't have this constant at that point. But anyway, that the A2 hexagonal lattice optimizes things would be equivalent, would tell us that, in fact, so CS2, this parameter when D is 2 should be this zeta function. We don't know that. It is interesting that because of a couple of recent results in 8 and 24 dimensions, we do know what CS8 is and CS24. CS8 is the zeta function for the E8 lattice, and CS24 is the zeta function for the Leach lattice. And this is due to results of, well, I'll give the Conankumar, Radchenko, Miller, and Vyazovska. This comes out of work that Marina Vyazovska did for packing in 8 dimensions. Also important, more important for us almost, are going to be the theta functions, which theta functions you get by periodizing a Gaussian function. And so if you consider all such periodizations, these will give you the theta functions. I'll write it up. In particular, if you periodize in 1 dimension with the Z lattice, just the integer lattice, then you get up to a scaling the classical 1-dimensional theta function. So theta functions come from lattice periodizations of Gaussians, and zeta functions come from lattice periodizations of well, okay, so I didn't really do, okay, I'm going to skip. There was one thing, don't ask me about, because I had to remove 0 from the other one. All right, here's just an example. So periodizing this guy, if you take a collection of bumps, that's C in a relatively larger scale. As C gets smaller and smaller, these bumps really overlap and you get other types of things. But anyway, this is a typical theta function for some lattice sum, okay? Now, what's interesting is that, and this is the observation of Henry Combe and Abhinav Kumar, who introduced this notion of universal optimality, in particular for energy on the sphere, but this has been now generalized to other settings, but it's by a basic result of Bernstein. You see that optimizing over the theta functions Part two, if you're optimal for all the theta functions, then more generally, you're optimal when you periodize any completely monotone function of distance squared that has sufficient decay, okay? So really what it says is that these functions, it's really related to this, completely monotone functions of distance squared are in the positive cone of these Gaussians. So if you optimize over all these, you get this bigger class. So if we have an endpoint configuration that's optimal for all theta functions for a particular lattice, then we'll say that that configuration is endpoint lambda universally optimal. There are several notions of universally optimal here that we're going to brush under the rug. If you want more details, I'm happy to do them kind of at the end of the talk. But we're going to focus on this problem of for a fixed cardinality and a fixed lambda, when universal optimality means that you're optimal for all of the theta functions for all C. Here is just, the Conankumar, Millo, Redchenko, Vyazovska result that E8 and the Leach lattices are universally optimal is very recent. And even the proof that that the integer lattice is universally optimal is non-trivial. And that's in the Conankumar paper. I think I'm ready to tag team. And okay. Nate.
Okay, so hello. Okay, so we've given the setup for this discrete energy problem now, where we have a fixed cardinality. So we're looking at a fixed number of points in the fundamental domain of some lattice, and we're asking, how do we arrange these points so as to minimize the energy for hopefully every single theta function, and that would give us then the wider cone of these completely monotone functions. So the candidate lattice, the natural candidate here is to take A2, which is the equitriangular lattice, and is conjectured to have many nice properties. And so this is sort of a natural candidate, and here we've got it pictured on the right side. And then our kernel, so the function to minimize over is periodizing one of these Gaussians, periodizing them by A2 and getting the theta function. And now the final thing is sort of what are your candidate configurations? What are the configurations that you hope are optimal? How do we suspect that arranging these points will lead to a ground state? And okay, a natural thing to do, since you think the actual A2 lattice is so nice, is to just take that lattice, scale it by, shrink it by a factor of n. So on the left here, we've got it shrinking by a factor of 2. And then if you intersect with the fundamental domain, you get an n squared point configuration. So here we shrink by a factor of 2, and then intersect with the fundamental domain of A2, and you get a 4-point 2 squared configuration. So the claim is that sort of this distribution of points is nicer, is a ground state as compared to some generic 4-point configuration like this. So that's going to be the claim. Here we've shown it for the case n equals 2, where you shrink the lattice by a factor of 2, but kind of the claim is going to be that you could, that not just this 4-point configuration, but every n squared point configuration for all positive n would also end up being your ground state. So that's like this very, there's lots of analytic asymptotic results that Doug was describing, and now we're sort of in this regime where we're considering this very discrete geometric problem. And so it has a little bit of a different flavor. Okay, so I guess one question is what's known in this regime where you take A2, you're considering a potential, which is this theta function, and we're looking at endpoint configurations. And there's not many rigorous results about these configurations, though it's easy to generate them numerically. And here in the case that n is 11 and our C, so the parameter of the theta function is 20. So that indicates sort of relatively distinct bumps.
This could be re-normalized. Yeah, so anyway, that's not the, it's definitely different because C is 100 in the other.
Yeah, and so C being 100, this indicates that the bumps are very
It's almost the
separated.
packing problem.
Yeah, this is almost the circle packing problem. And you can see sort of that the points arrange themselves sort of in these nice hexagons with the center removed. So, or this nice honeycomb with the center removed. But again, these are numerical, these are numerical local minima, and these would be extremely difficult to show that they're actually global minima. So, okay, are there any actual rigorous results? There are some basic things that have been done. So in the case that n equals 3 and n equals 2, so we're just placing 2 or 3 points inside the fundamental domain of A2, we have universally optimal configuration. So here's the n equals 3 universal configuration with points here, here, and here. And okay, this is a result of a former student of Doug's in 2015 or so. And then likewise, with n equals 2, we get a similar universally optimal configuration. But this, that leaves a lot to be done, given that our original hope was to take configurations where we shrink by a factor of n and get an n squared point configuration, right? That leaves a lot to be done, given that we only have the 2 and 3 point configurations. So the first kind of result we have towards this end is the n equals 4 case, so 4 points, and we obtain this configuration as on the previous slide by shrinking A2 by a factor of 2, and then intersecting with the fundamental domain to get 4-point configuration. And we can actually show rigorously that this configuration is universally optimal, and so is maybe a proof of concept that this larger that as n grows, these n squared point configurations are universally optimal. And so I guess for the rest of the talk, we'll talk about, how do you actually go about showing these things in a rigorous manner. And I guess maybe also worth warranting is, or worth explaining is, why are you interested in the equitriangular lattice and finding these finite universally optimal configurations? And the reason sort of ties back to a big conjecture of Conankumar from 2007, where they conjecture that in this sort of larger sense, which Doug said will sort of wipe under the rug, that the equitriangular lattice A2 is universally optimal in R2. And that's a big open problem. That's maybe the biggest open problem in the area. And so if you were able to show that these discrete point n squared point configurations that we're hoping are universally optimal, if you're able to show that those are actually universally optimal, well, it would give you this large conjecture of Conankumar that's been open for, I guess, 15 years now. So, okay, well, I guess Doug mentioned this before, recently it was sort of stated in terms of these completely monotone functions by Conankumar about A2 being this very special lattice in the plane. But conjectures about how it's very special are longstanding, and I think in the 90s, Saf and Couillard's talk about how it's optimal in some sense for the Riesz potentials. So this is kind of the motivation for why to consider this discrete energy problem, because it gives you a way to get at this larger conjecture about the optimality of this lattice in the plane.
Okay, and we're going to kind of go quickly through some of it because I see we have more slides than we have time. I do want to talk a little bit about, so first of all, the dual lattice is one way to specify it is these are the points whose inner products with elements in the lattice are integer valued. These are important, useful in parameterizing Fourier series in the lattice setting. And so we're going to just quickly, the linear programming bounds always have some kind of orthogonal transformation underlying them. We're going to write this in the lattice sense. So if we take some function g that has non-negative coefficients in its Fourier expansion. So you take a periodic function. So I'm thinking of G as being a periodic function, or you can think of it as just being defined on the fundamental domain. It has non-negative Fourier coefficients. Then you can get a nice estimate, a nice lower bound for the G energy for any collection of points omega n. And the double sum, you have to divide into, you can write this as a double sum. You pull off the terms on the diagonal. That's where this ng of 0 comes in. And then the other terms, you can write, there's a conjugation, you get this, okay. Now, the assumption that the Fourier coefficients are non-negative allow us to throw away all of the non-zero terms in that sum. And when you, and that the 0 term involves an n squared times G hat 0, and you get this lower bound. So we throw everything out that depended on the configuration. So this can't ever work. Okay. So the way we would apply this to an energy problem is if you're given a periodic potential F and you find a lower bound for F on the fundamental cell, then this gives you a lower bound on the minimum energy because F is bigger than or equal to G, means the energy of any endpoint configuration, the F energy is bigger than or equal to the G energy. And then the G energy, you minimize this expression over omega n. There's no omega n on here. So this is the linear programming bound in this setting. Okay, so I'm going to kind of whip through this. These linear programming bounds come up, they originally developed kind of in the context of coding theory, particularly on the sphere, but in other settings by Delsart and collaborators, and then adapted to energy problems by Hardin and then Hardin and Andreev. There's a collection of papers. And then more recently for energy and packing problems in Euclidean space. And Marina Vyazovska's paper showing the optimality, using these bounds to show that the E8 lattice gives you the densest sphere packing in 8 dimensions, then led to the universal optimality results. Just quickly, in order to show that a particular configuration is optimal, then we need that these inequalities become equalities. And so in order to show, in order for the F energy of a given configuration omega n to achieve this linear programming bound in order to get to show optimality of omega n, then there are two things. First of all, you have to have G and F agree at all of the differences coming from omega n. So that gives you a equality, the first equality. And then the second equality, all of the terms that we threw away Fourier coefficients times these moments, one or the other has to be 0. So both of these have to hold in order to get to achieve equality of this lower bound. That just says the same thing. I'm going to let Nate take over now. So I would say, I do think this is a good point. But you go ahead though.
Okay.
Since you made us.
Yeah, sure. So, okay, right. We needed, for this to actually provide not just a lower bound, but a sharp lower bound. So to not just, so to actually show that the configuration is optimal, you need to turn these inequalities to equalities. And so, we get these two conditions. And ideally, these are necessary conditions that your upper bound, your lower bound G is actually interpolating F at these differences of points. And so each one of those provides a necessary condition. And here, every time this second term, this moment is equal to 0, well, that allows your corresponding Fourier coefficient to be non-zero. And so you can think of these as sort of every time this is allowed to be non-zero, that's a degree of freedom. And every time that G has to actually interpolate F, that's a necessary condition. And so to have some flexibility in setting, in finding a G that makes these inequalities into equalities, you'd like not very many of these necessary equality conditions. So you'd like relatively few differences, X minus Y, for points in your configuration. And you'd like lots of freedom to choose the Fourier coefficients of G, which means that you'd like lots of these moments to vanish. And so these are both properties of the configuration, the hypothetical configuration, optimal configuration omega n. And so if you have an omega n that has relatively few differences and then lots of these moments vanishing, and you suspect it's optimal, that's kind of a good, gives you a good candidate for the linear programming bounds. And okay, that's kind of exactly what's going on with this 4-point configuration, which you obtain by shrinking the A2 lattice by a factor of 2 and then intersecting with the fundamental domain. It has the minimal number of differences and it has sort of a maximal amount of these moments vanishing. So that brings us to kind of our theorem, which is that I mentioned before, but that this 4-point configuration is optimal for every kernel which periodizes one of these Gaussians, and that gives us then this wider cone of potentials which are periodizations of completely monotone functions. And again, this is sort of relevant to the larger program of showing that if this 2 was an n, if you get an n squared point configuration, that those would also be universally optimal. So that's the first theorem, and we use the linear programming bounds to get it. I guess it's maybe also worth noting that when you're trying to show something's optimal, you're looking for upper and lower bounds on the energy. Well, upper bounds on the energy are going to be on the minimal energy are easy to get because the energy is an infimum. So any configuration, any plopping down of 4 points in this fundamental domain is going to give you an upper bound on the energy. But it's the lower bounds, it's finding something that's, some number that's better than any possible energy you could get from placing 4-point configurations. That's the difficult thing to get after. So that's why the linear programming method is sort of special. So I guess we can talk briefly about how do you go about proving that this is optimal via the linear programming.
Let's get the polynomials.
Yeah. So, okay, using the linear programming bounds, you're looking for this G, which is staying below our theta function f. It has non-negative Fourier coefficients, and it equals and it actually interpolates f at the differences of points. And because our configuration is so special, actually being equal at differences of points is the same as being equal at the non-zero points. And here's kind of where the special properties of the A2 lattice come into play, which is that A2, it's not just invariant with respect to lattice translations, but it also has the same symmetries of the lattice. So the A2 lattice has all the symmetries of a regular hexagon. So one of its fundamental domains is pictured below in blue. And so you can see it has this order 12 group of symmetries where if you rotate by 60 degrees, it stays the same. If you reflect, through any one of these bisecting lines, you get the same thing. And so that allows you to restrict this interpolation problem to not the entire fundamental domain where you started, but just this 1/12 of this red triangle here. And so okay, we can do that as long as our interpolant, as long as our interpolant G, this magic G function, is, has the same symmetries that F does, that it has the symmetries of the A2 lattice. So a question becomes, how are you going to get these functions? How are you from the Fourier basis? How are you going to get functions which have the symmetries of the A2 lattice? And okay, that's where these nice polynomials come into play. So anytime you want to get a function which is invariant with respect to a group, one natural idea, is to take a group average. So to take the function and average out by the symmetries of the group, and that's exactly what we're going to do here. So given a vector in the dual lattice V, we'll define its generalized Chebyshev polynomial CC sub V to be the group average over all the compositions of symmetries in G2, which is again this group of symmetries of the regular hexagon. And so if you do that, now you have these candidate building blocks of functions which are invariant with respect to the hexagonal lattice. Invariant with respect to the symmetries of regular hexagon, and so make the interpolation problem have sort of many less degrees of freedom. And what's remarkable about these polynomials as a result of, I guess, Yuan Xu and collaborators, which is that all of these they're called polynomials for a reason, and that's because all of these are going to be polynomials in the most basic Chebyshev polynomials. So yeah, that's a little bit technical, but allows us to, under a proper change of variables, turn things into a polynomial interpolation problem. So okay, which now you've got these candidates, these CC sub V. These are not just invariant under lattice translates, but since you took the group average, they're invariant under the symmetries of the regular hexagon. And so we want to know which ones we could use to use the linear programming method. And okay, well, we can do that if we're only using Fourier coefficients which are allowed to be non-zero. In other words, if the corresponding moment vanishes. And again, because our configuration is so nice that it's just the scaled lattice, we were able to use lots and lots of these generalized Chebyshev polynomials, which is sort of what this proposition is describing. So there's a lot of freedom, in building up this G because the configuration is so nice. And in fact, as n grows large and we take not just 4-point configurations, but 9, 25, so on and so forth configurations, we have even more freedom in building up this interpolant. And so, okay, there's lots of freedom in building the interpolant, but you need to have a good understanding of the function to be interpolated. And so that's, I guess, you want to jump in here? I don't know if this is too technical. Yeah.
No, well, okay. So we're going to I'm going to skip through some of the technical details, but we use properties of the theta function in particular, that theta tilde is a nice function in terms of this arc cosine parameter, and the t these become now polynomials. Okay, yeah. So in the end, we are working with a bivariate interpolation problem in terms of T1 and T2. These variables, yeah.
I think it's on the next page.
Let's see where, okay, yes. These minimal polynomials can be written nicely in terms of T1 and T2. And T1 and T2 are these cosine functions, okay? Then the remaining polynomials, higher degree polynomials, can be written as polynomials of these. So we have a bivariate interpolation problem. Because of all the symmetries it ends up with only one for 4 points. There's only one interpolation point that we have to worry about, and that's this is in the T1, T2 domain. It becomes, but it's a bivariate problem, so we need not only the value, but we need conditions on the tangent plane at that point. Okay. There are, so for us, usually we've so far in the examples, we've usually been able to show the positive definiteness that we can produce an interpolant with non-negative coefficients in this, but it's usually the state proving, even when we numerically see it, proving that it stays below on the domain has been the part that gets technical. And so I'm not going to, for the 4 point, that's definitely the case. That's the most technical. We use properties of the triple product formula. There's classical kind of results about theta functions that come in that I'm not going to talk about. This will, I think, be my last slide other than some, so we're a bit more excited about another sublattice. Instead of taking the scaled versions of the sublattice for A2, there's another kind of interesting square root of 3 sublattice. So in other words, this is Z cross the square root of 3Z. That's a natural sublattice of A2. And we're looking at optimal configurations that come from taking scales of that lattice or scales of the A2 lattice restricted to this sublattice. So for example, there are 2 families that come out. We have a family that goes like 2m squared, where m is the scaling, and then there's another family 6m squared. For the for 2 points, then it becomes an almost triviality that these, amongst all of the 2 point periodic configurations with respect to this Z cross square root of 3Z lattice, that this is universally optimal. That turns out to be not, that's just an observation almost, but it's much easier than the 2 points that Eugen Su did. We're in the midst of and I really thought we had it, but we can't. We still don't have all the details nailed down. That for 6 points, so for 6 points that this is the scaling that you get. There's a 6m squared family. So if you extend this, this is the scaling of the A2 lattice. If you extend it by this Z cross square root of 3. By the symmetry, we end up having 3 interpolation points where we have to check things. And we're able to do it for C that are relatively small. And we don't quite have it yet for the remaining value. We're typically, we get it for C small, then we do different expansion for C large, and then we try to meet in the middle. But we haven't finished this. So we believe, yeah, so maybe next week, now the class is ended, we'll finish. We'll have, this seems very close though. that we get universally optimal for this 6. We see patterns start to evolve, but we don't yet have the general case. So anyway, I'm going to stop there. Thank you for your attention, and let me know if there are any questions.
All right.
Nate is happy to answer any questions.
All right, let's smash that reaction button and thank the speakers.